Welcome back. We are going to look at examples of conservation momentum in terms of problems. We've already defined the conservation momentum as the total momentum of a situation before and after some collision or explosion must remain constant. But we want to look at this more from a mathematical or a number standpoint. So I'm going to select my pen here and say, well, the sum of the momentum initially must equal the sum of the momentum finally or after some collision. That's a simple way of showing this as a formula rather than as a statement. So let's just give you a real easy example. I'm going to make a cannon here. Here's the wheel of the cannon. So this thing is kind of free to move. And for effect, I'll put a fuse on here. But if we look at this cannon, this basically has no momentum. And that's because the velocity is equal to 0. If we kind of go after, this cannon is going to recoil. You wouldn't want to stand behind a cannon that just launched a cannonball because it's going to be moving backwards with some velocity towards you. We hopefully understand that now there's a cannonball that's moving forward with some velocity, which implies that there's momentum now. Before there was no momentum, but now there's definitely momentum. However, the momentum at the end must equal 0 because of our conservation statement, which means this has some negative momentum, this has some positive momentum. But when I add this momentum up, the final momentum is going to be, the positive momentum of the ball. Oops, not PB. Let me just try to undo that. Momentum of the ball plus the negative momentum of the cannon. Those two things would cancel each other out or equal 0. So whatever momentum this has going forward, this has the same amount of momentum going back. This will have a much greater velocity because it has less mass. Remember, momentum is equal to mass times velocity. This will have a greater mass, which means it'll have much less velocity as it goes backwards. So that's just a real simple way of doing conservation of momentum visually. Now let's work through some example problems. And our first one would deal with two pool balls, or billiard balls, you want to call them that. One is a blue ball moving to the right with an initial speed of 3 meters per second, and a red ball that is at rest. Afterwards, the blue ball is still moving to the right with a velocity of 1 meter per second, but now we don't know what's going on with our red ball. And we want to mathematically kind of see what this is. And some of you might be able to figure this out without doing anything, but we're going to show you the math and see if we can verify your guess if you're one of those people. Again, initial momentum equals the sum of the final momentum. The sum of the initial momentum equals the sum of the final momentum, which in this case would be the momentum of the blue ball initial plus the momentum of the red ball initial is going to equal the momentum of the blue ball final plus the momentum of the red ball final. Now I'm going to leave these BIs and RIs off as I go to the next step because I think we get too many letters here if you keep subscripting everything. We're just going to go to MVs, mass of the blue, velocity of blue initial, mass of the red, velocity of the red initial. We can always check here to kind of see what we're looking at. This is our initial red velocity, which would come from over here. And do the same thing on this side. So our next step is filling in our variables, 0.16 kilograms times 3 meters per second plus 0.16 kilograms times 0 meters per second, which I'm sure many of you have already figured out is going to cancel out to be 0, is equal to 0.16 kilograms times 1 meter per second plus 0.16 kilograms times v meters per second. We don't know what this velocity is. Now there's a couple different things that we can probably take note of. One is we have a common value to every single term in the formula. We can cancel that off. Makes life a little easier. I'll cancel here even though it really doesn't make a difference. Cancel it off, cancel it off. So now we end up with 3 meters per second plus 0 is equal to 1 meter per second plus v. This becomes a very simple problem. Well, what plus 1 would equal 3? And that answer is just simply 2 meters per second is equal to v. Should be positive because this red ball will then continue to move to the right. make our total momentum equal to 0. Now, you can't always do that. Even with our cannon example from before, we knew the cannon had a different mass than the ball that we're shooting, and therefore would not be able to cancel the mass out if we did those collisions, or the calculations. Here is a different scenario where everything's the same, so we could cancel those out. Even if we didn't, we would still get the same answer. Second example here is a student on a skateboard with a total mass of 65 kilograms catches a 400-gram football that is moving at 25 meters per second. Okay, so we have a person here on the skateboard, so we're not drawing a very straight line, and that person's having a football thrown towards them. The velocity of this football is 25 meters per second, moving this way, and the mass of this is equal to 400 grams, which hopefully we then realize needs to be 0.400 kilograms. This person has a velocity equal to 0, and their total mass is equal to 65 kilograms. Now, I think drawing pictures like this can be very beneficial. It helps you organize your data. You can kind of see what goes with what very easily. And I'm just going to switch colors here as I kind of go to the calculation part. And it's the same idea as before. The sum of the initial momentum must equal the sum of our final momentum. Now, kind of just draw an after picture here, we would guess that this skateboard and this person are probably going to be moving this way with some velocity, but we don't know what that velocity is. And I guess I should add my person who now caught the football. Sorry about the bad picture, but you can see this is going to be moving to the right. The question is, what is the velocity? So again, if I start filling in my things here, the momentum of the football initially plus the momentum of the skateboarder initially is equal to the momentum of the football final plus the momentum of the skateboard final. And again, now we're just, okay, MV plus MV is equal to MV plus MV. Start plugging in our numbers now. Football has a mass of 0.4 kilograms times 25 meters per second plus the mass of the skateboarder, which is 65 kilograms, times 0 meters per second, is equal to 0.4 kilograms times v meters per second. And I guess the one thing we notice here is that both velocities will be the same because he's holding on to that football, plus 65 kilograms times v. So, okay, well, we have a common variable with two terms here. We can combine these, and we're going to say, okay, well, this is going to be v times 65 plus 0.4 kilograms, which will be 65.4 kilograms times v. Now, I'm kind of running out of room, and you can see here this cancels off, but this 0.4 times 25 turns out to be 10 kilograms times meters per second. I guess I can write that same 10 kilograms times meters per second here. What we need to do is divide this number into this. Now I'm going to have to write that velocity up over here, which is going to be 0.15 meters per second. And it's going the same direction as the football was, which in our picture is going to the right. That should make sense. The system became much more massive when the person caught the ball. And now the velocity must be much less than the original momentum of the football. So again, you just got to look at things that can be combined and kind of combine like terms sometimes. It seems like we might have two unknown velocities over here, but if you kind of think through the problem, that v is the same for both because they're both moving to the right. Last problem is, again, we're going back to our little skateboard and the student example, and again I'm going to attempt to draw, my football's been really bad. Find my best one. That is still moving to the right with a velocity equal to 25 meters per second. And it still is going to have a mass of 0.4 kilograms. Our skateboarder is still here, but this time they have a velocity. And it's 0.10 meters per second. The mass of this person is still 65 kilograms. And they will catch it just like before. You know, so this is kind of our before if you want to draw an after picture. That's totally up to you. Here's a football. You know, but what is the velocity at this point? We kind of concluded from the previous problem, the mass of this will be 65.4 kilograms But what happens to the velocity, or what is this going to be doing? Is this going to be the prevalent momentum, or is this going to be the prevalent momentum, meaning the one that's going to be bigger than the other? Because whatever one's bigger, that'll be the final direction. And we can just simply use our formula to figure that out. So I'm going to switch colors again and say, all right, the sum of my initial momentum is going to equal the sum of my final momentum, which is just going to be, okay, momentum initially of the football plus the initial momentum of the skateboarder is equal to the final momentum of the football plus the final momentum of the skateboarder. I think I did these backwards, but I is using initial, F is final, and then football and skateboard shouldn't be too bad to handle. MV plus MV is equal to MV plus MV. Now, we have to make something negative in this problem because we have one velocity going this way and one going that way. So if we just want to define positives going right, then this becomes a negative 10. So again, filling our numbers in, we're going to have 0.4 kilograms times 25 meters per second plus 65 kilograms times a negative 0.10 meters per second is equal to 65.4 kilograms, and that's kind of using the same idea we had from 4 times v. So now we have to go and figure out which one of these is going to be greater. Well, this times this is going to be 10 kilograms times meters per second. This is going to be, oops, mistake there, let me take that out. 10 kilograms times meters per second minus, we can just figure out, it's just going to move the decimal one place that way, 6.5 kilograms times meters per second. That equals 65.4 kilograms times v. Our overwhelming momentum here, the greater of the two momentums, is from the football. So now when I take these two things and subtract it, I get 3.5 kilograms times meters per second is equal to 65.4 kilograms times v. And then when I divide each side by 65.4, my velocity is going to equal a positive 0.054 meters per second, which basically means that this football is able to hit the person on the skateboard and they end up moving backwards a little bit. So at a relatively small speed, it's 5 centimeters per second, which is a pretty small speed, not really great. But again, it's sometimes hard to tell. I would probably initially think that the person just has so much mass that the football would not be able to knock them back. But it turns out that's not the case. And that's why we have to be careful sometimes when doing these kind of momentum problems, that we don't make guesses. We use the math to kind of help us form opinions and understanding. So that's our final problem with conservation of momentum.